This is the first topic of the course Probability and Stochastic Processes. In this topic, we are going to talk about the probability spaces. A probability space is a mathematical structure that contains two components. The first component is called the sample space. A countable sample space S is a non-empty countable set, any non-empty countable set. Now, an element omega inside of this set S is called an outcome, and any subset E of S is called an event. So, both sample space and events contain basically outcomes. The second component of a probability space is a probability function. The probability function defined over a sample space S is a total function PR that maps an element of S to a real number that satisfies the following two conditions. The first is for each outcomes omega, the probability of this omega must be more or equal to 0, and the sum of all this probability of omega must sum up, and it must be equal to 1. Now, any function that satisfies these two conditions is basically a probability function. Now, these two components, the sample space and the probability function, forms a mathematical structure. So together they form a mathematical structure which is called a probability space. Now, probability space is basically our abstraction of probability. This is basically our model. Previously, we have seen the definition of the probability of an outcome when we define the probability function. Now, this definition can be lifted and generalized to the probability of event. Given an arbitrary event E, the probability of event E is defined by the sum of all the probability of omega inside of this event E. In the next part, we are going to look an example of how to apply this probability space to solve our real problem. A probability space is basically a mathematical tool. Now, what you're going to do is to transform any problem we encounter, any probability problem that we encounter in real life, and then transform it into a probability space. And once we have this probability space, all we have to do is just to solve it. This is one of the examples. On the September 9th, 1990 edition of Parade magazine, Madeline Forsavant received the following questions in a letter. Suppose you are in a game show and you are given the choice of 3 doors. Behind one door is a car, behind the others, coats. You pick a door, say number 1, and the host, who knows what's behind the doors, opens another door, say number 3, which has a goat. He asks you, do you want to pick door number 2? Which means that asking whether you want to switch or not. The question is it to your advantage to switch your choice of doors? Now, this is a probability problem that we encounter in real life. So in the rest of this discussion, we are going to see how to transform this into a probability space and then solve it. Now, the problem is this problem itself is not actually 100% clear. The question is a little bit ambiguous here and there, and hence we must make several assumptions. The first is that the car is put behind one of the doors randomly and uniformly. This is not actually explicitly specified in the questions, but this is a fair assumption. Because this is a game show, we expect that the card is put behind one of the doors randomly and uniformly. There are two things here. Randomly. Randomly means that we put the card behind the doors in no apparent patterns. So in tonight's game, we may put it behind door A, tomorrow's door C, and so forth, without any pattern whatsoever. Uniformly, on the other hand, means that if we have several choices, then the probability of selecting each of these choices must be the same, must be equal. So in this case, for example, because we have 3 doors, this means that the probability of us selecting one of the doors must be equal to 1/3. So this is what uniform means. The second assumption is that the player selects one of the doors also randomly and uniformly, independent of the card's location. Of course, because the player is assumed not to know the card's location. The third one is after the player selects a door, the host must open a different door. So this is basically her SOP, as a standard operating procedure. This means that it cannot be the case that tonight in the game show the host open it and tomorrow not. So this must be done every time the game is carried out. The host must open a different door with a code behind it and then offers the player to remain on the selected door or to move. If the host has alternative for the door to open, she must select one of them randomly and uniformly. Now we can define properly our probability problem, which is what is the probability that a player who decides to move her choice gets the card. Now every probability problem always involves random experiments, processes, or games. This is basically the keyword. We are going to look deeply into this. We are going to look at random experiment. Random experiments is a random experiment is an experiment whose outcome cannot be determined beforehand, whose outcome happens randomly. Now to solve any probability problem, we must answer two questions. One, how do we model the situation mathematically? And once we have the model, how do we solve the resulting mathematical model? In the next part, we will discuss a 4-step method to answer any questions of the form what is the probability of something and so on. Now this is a method. This is basically what we are going to do to perform the model, to obtain the probability space and solve it. Now the 4-step model, of course, contains 4 steps. The first step is determining the sample space. Our first goal is to identify all possible outcomes of the experiment. Typically, experiment involves several quantities that are determined randomly. And this is what we have to look for. Quantities that are determined randomly. Look at this in every probability problem, and if we manage to identify them, then we will be able to identify all possible outcomes. List first the quantities that are determined randomly. For instance, in our example, in the multi-hole problem, we are dealing with 3 such quantities, namely the door number for the car. We assume actually that this must be done randomly. The second one is the door number originally selected by the player. Also, we assume that the player select this randomly. And the last one is the door number opened by the host with code behind it, of course. Now, once this quantity's value is determined, then we have a fixed outcome. A possible configuration of all these randomly determined quantities, so once you fix their values, becomes an outcome. This is an outcome. An outcome is a possible configuration of all those randomly determined quantities. And the sample space is simply the set of all possible outcomes. We can often visualize the outcomes as a tree diagram, and this will simplify us and allows us to look at these outcomes systematically. This is an example of the tree diagrams. Now, if you remember, there are three randomly determined quantities in our problem. The first one is the car location. So to form our tree diagram, first we have the root of the tree, and from this root we have branching, and the first branching that we have is determined by the car location. Because there are three possible doors, we denote this by door A, door B, door C. This means that originally we are here before we perform the game, and then the first step of the game is to determine the location of the car. Now there are three possibilities, and we list it here, and we have to select it, one of them. Now once we select the location of the car, the next one is the player's initial guess, and there are also three possibilities for this, so we make further three branches out of the original one. Now the last part, the third quantity, the third randomly determined quantity, is a little bit special. Now if you notice, right now there are not three choices available for us, because there is a reason for this. Let's see for this example. Let's see for this branching. This means originally the car is put behind door A, and then the player select this door. Now of course the host cannot open this door anymore, because the player has already selected it. Furthermore, the car is behind that door. So this means the host can only open either door number B or number C. So this means that there are only two alternatives for the host to open. Now let's look at this other example. In this case, the car is put behind door A, and then the player's initial guess is C. Now in this case, the host cannot open A because it contains the car, and then the host also cannot open C because it is already selected by the player, and the only alternative left is to open B. Now each leaf here, these are the leaves, in the tree diagram represent an outcome, and the set of all these leaves represent the sample space. So all of these leaves are the sample space. Now we can label each outcome as a sequence of the components to help us. So this is a sequence that contains of three components. The first component is the door for the car. Second one is the door selected by the player, and the third one is the door revealed by the host. Now it is easy to see that our sample space contains these sequences. The first one, for example, is AAB, AAC, Well, AAB means the door for the car is A, the door selected by the player is A, and the door revealed by the host is B. These also correspond to our previous tree diagram. So in our tree diagram also we have this. We have this A, B. So right now we can actually label this outcome as a sequence A, B. Now it is quite clear for us the interpretation of the tree diagram. Well, the interpretation of the tree diagram is basically an experiment. Yeah, so this is basically an experiment. An experiment can be considered as a traversal along a path from the root to the leaf where branching is done randomly. Now we are complete. We have labeled all of the leaves with the outcomes. In the next step, step 2, we define the event of interest. A set of outcome which is a subset of the sample space is called an event. An event can normally be characterized by daily conversational description. For example, the event corresponding to daily conversation, daily description, the car is behind door C is given by these 4 outcomes. This is a set which contains 4 outcomes, namely CAB, CBA, CCA, and CCB. Well, this basically corresponds to all the branching that originates from this one. Well, this basically says that the car is put behind door C. This is an event. Now for our example, our event of interest is a little bit different. We are looking for the event characterized by the player chooses to switch or to move and gets the car. What is this? Well, if we look back again to this tree diagram, then this event of interest, let's see one of the examples is ABC. So let's look at this example, ABC. What happens here? Well, originally the car is put behind door A, and then the player select B, and then the host open door C. You see there, so the door that are not open yet is A and B, and now if the player decides to switch, then she must switch to A, and if she switch to A, then she gets the car, which means that she wins. So this is one of our event of interest, or one of the outcomes inside of the event of interest. And similarly, with similar reasoning, we can find other outcomes which is inside of event of interest. There are 6 of such outcomes. Yeah, so those outcomes are ABC, ACB, BAC, BCA, CAB, and CBA. Look that precisely half of the outcomes are members of our event of interest. Now you will probably think that the probability of the event is then 1/2 because half of the outcomes are their member. But this is wrong. This is because the probabilities of all outcomes are not the same. And this is what we are going to see in the next part. What is the probability of these outcomes? This comes in the 3rd step. In the 3rd step, we are going to determine the outcome probability. In this step, To each outcome, we assign a probability that represents our expectation of the occurrence of the outcome. Where do we get this probability? Well, this probability is determined by the phenomenon that we are modeling, and not something that we can obtain mathematically. This is basically based on our observation of the real life. We look at real life and we model this and we make assumptions and so forth. This is the probability. So this means that the probability is something that we ourselves determine. We fix it. Of course, we don't fix it arbitrarily. We have to match it with something that we look in real life. And this is usually involved our assumption. Now the sum of all this outcome probability of course must be equal to 1, because every experiment that we conduct always produces an outcome. Every experiment always produces an outcome. Okay? Now if we look back again to our assumption, if you are careful, then you have seen that in our assumption, we are always talk about uniformly. Uniformly means that with the same probability. Now this step contains two sub-steps. First one is 3a, assigning probabilities to H. First, we assign a probability to each edge of the tree diagram. This probability is something that is determined by the assumptions that we made on our mathematical model. For instance, if you remember, we have an assumption that the car is put behind one of the doors randomly and uniformly. And the important part is uniformly. Uniformly means that for every alternatives, we are going to give all of the alternatives the same probability. Therefore, because there are three alternatives, for example, every edge on the first level are assigned the same probability, namely 1/3. So we are going to give the probability of this edge 1/3, 1/3, and 1/3 because of our first assumption. Our assumption says that the car is put behind one of the doors randomly and uniformly. When in a similar manner, we are going to assign the probability of this edge in a similar way. Pay attention to this one. Now in this case, because there are only two alternatives, to make it uniform, then the probability of each alternative is equal to 1/2. For this one, is an extreme case because there is only one alternative, then the probability of the edge is equal to 1. Now once we have this, we assign the probability to each edge. The next sub-step is calculating the outcome probabilities. Next, we transform the edge probabilities to outcome probability, and we are going to use one rule for this. The probability of an outcome is equal to the product of the probabilities of all edges traversed along the path from the root to the leaf that represent the outcome. This is a rule that you have to remember. Where does this rule come from? Well, we are going to look at it in the next topic when we are dealing with conditional probability. For the time being, just believe in the rule. So what you're going to look then, just to apply this rule, namely, we will compute the probability of an outcome as the product of the probabilities of all edges traversed along the path. So let's look. We return again to this tree diagram, and to obtain the probability of the outcome AAB, then all we have to do is just to compute the product of all the edges along the path from the root to the leaf. The ages is A with probability 1/3 and A with probability 1/3 and B with probability 1/2. So the probability of this outcome is equal to 1/3 multiplied by 1/3 and multiplied by 1/2, which is equal to 1/18. So that's it. In a similar manner, we can compute the probability of all the outcomes, of all other outcomes. Let me give you another example. For example, this one. The probability of outcome A, B, C. So the probability of the outcome A, B, C is equal to 1/3 multiplied by 1/3 multiplied by 1, which is equal to 1/9. Okay. Now based on this, we have already had our outcomes probabilities. Okay. So for example, the probability of the outcome AAB previously we have seen is equal to 1/3 multiplied by 1/3 multiplied by 1/2, which is equal to 1/18. Okay. Now when we calculate the outcome probabilities, we in reality is defining the function that maps each outcome to a probability value, and this is what we call the probability function. This is the second part. This is the second component of our probability space. Previously in the first step we define the sample space. Now in this step we define the probability function. As an example, we just basically define the probability of ABC is equal to 1/9. We perform this mapping. Now we arrive at the last step, namely step 4, calculating the probability of the event of interest, of the event that we are interested in, that will answer our questions. The last step is calculating the probability of the event of interest. Now the probability of event E, like previously we have seen, is denoted by PRE, is the sum of all the probabilities of all outcomes inside of the E. Yeah, so this is basically our definition, our generalized definition. So the probability of event E is equal to the sum of all the probability of omega for all the omega inside of the E. We have seen this before. And then we have also seen that our event of interest is the player chooses to move and gets the card. And this event consists of these outcomes: ABC, ACB, BAC, BCA, CAB, and then GBA. We can look back again to this tree diagram for that. These are the switch wins. So the player decides to switch and wins the game. ABC, ACB, BAC, BCA, CAB, and CBA. Now, each one of them occurs with probability 1/9. So this is basically our catch. Why the probability is not equal to 1/2. Now if we sum them all up, then this is basically 6 multiplied by 1/9. This is 2/3. So this basically answers our questions. The probability, what is the probability that the player chooses to move and gets the car? The probability is 2/3. Now, this is not actually quite intuitive. This is a little bit counterintuitive. We actually expect that the probability is 1/2. But careful mathematical modeling that we have conducted reveals that this is not the case. So it is actually to your advantage to switch your choice of door if it is offered to you, because this will improve your probability of winning. It improves from 1/2 to 2/3. And this is the end of the first topic, probability spaces of the course, probability and stochastic processes. Thank you.